bit up down counter with 4 of those MSB bits being displayed. So here is my module with 3 inputs, that is clock, reset and direction. Direction, as you can see, if it's 1 it will count up, and if it's 0 it will count down. And here is an output for called as count, which basically displays the top 4 bits of the counter. Here I have defined a 32-bit pre-count register, which will basically store the 32-bit value of the counter. Now if this is a active low reset module, so if reset is put at 0, the pre-count register will be immediately filled with zeros or cleared out, basically reset. And this checking will be done at every positive edge of the clock or negative edge of reset. Now when we come to direction, if the direction is 1, the counter will go up, else the counter would go down, and the top 4 bits of count are taken out from pre-count register 4 bits. So now I have went ahead and already compiled the design. Now let us see the ALMs being used, number of ALMs being used. As you can see, there are 17 ALMs being used. To get a more detailed report, let's see here. We got 17 ALMs being used and 34 ALUTs being used. Now to test the same, I have written a test bench. Now I've divided it into 4 cases, where first the reset is held for 100 nanoseconds, where the direction is kept as 1. Since the reset will be on, it doesn't matter. And then after 100 nanoseconds, the reset is released and the counting up will begin. And then after 200 nanoseconds, I've reversed the direction of counting. And after 200 nanoseconds, I've again held reset for 60 nanoseconds, and later I've released the reset with the direction being low. And I'll be printing all these values at every positive edge of the clock, such as time, reset, direction, count, and the pre-count register. Now I've also written a SDC or timing constraint file, where I've defined the clock here, which is of a period of 20 nanoseconds, and derived PLL clock here means that it basically tells the clock blocks, or any clock entity that is being used in my design will derive its, or will have the constraint same as the PLL in the main board. And clock uncertainty here refers to clock jitter and other things, other uncertainty values in clock, which must be taken into consideration while for the setup and hold time violations. So it's telling to include all those uncertainties. So I went ahead and simulated the same. As you can see, I have simulated the same, and let's look at the result. See, as the reset is being held, the values of pre-count register and the 4-bit MSB or the count is being held at 0. So as I said, if you remember, after 100 nanoseconds, I had released the reset and increased the direction to 1. Now this direction being made 1 will be taken up during the next positive edge of the clock, which will be at 110 nanoseconds. Since it will be sampled here, the value will still be 0, and this clock being the direction being made 1 is sampled here. So at the next rising edge of the clock, the value starts increasing. Hence we have this normal functioning, or where you see the case of even after direction being made 1, there is still zeros. And then same goes with countdown. After 200 nanoseconds of that, I had basically let go of the direction. Now this being 0 is sampled at this instant, so here the count would have already increased, and direction being made 0 is sampled here. So at the next rising edge of the clock, the count starts going down, and that's this case. As you can see, the count has increased 1 2 3 4 5 6 7 8 9, and then after the direction being sampled 0 here, as you can see, the count has gone down from 8 to 1. And then I've held reset for 60 nanoseconds again, so you can see all zeros. And then I let go of the reset here, which is being sampled here, which was sampled here. So the next value, the reset being released, is taken into consideration here, and since it's already kept at 0, it starts counting downwards. As you can see, the values are going down. Thank you. So the compiled design or the netlist view. So here I'll be showing the netlist view. The RTL view would be looking like this, where you are just subtracting here and adding here based on direction here. So this will be the basic RTL view of the design, and here I'll have the post fitting look at the design, where you can see the design is being mapped onto the FPGA board. So here it uses adders. Basically this adder will use the data from here and then the direction as one of the inputs, and then it uses the previous value pre-count as one of the inputs, and then this sum will be taken back here, and this cout will be used for the next stage to calculate what should be the value for the upcoming stages. So that is how the design is being mapped, and here is the output. As you can see, the last four bits are taken, last four MSB bits are taken for count. Thank you. Dumping the program on the FPGA. So what we do is first we plan out the pins that we're going to use on our FPGA. That is what is being done here. The clock is given to pin A14, which is D4, and these three are the LED outputs which have been mapped fully, and the direction and two other input pins that are also being mapped here. So this having been mapped, I've already recompiled the program to show you it's done. Now I'll be dumping it on my FPGA. As you can see, it shows there is no hardware. Going to be turning on the FPGA board. The D1 SoC board. Now we auto detect. Now since I had already loaded this file previously, I'm going to compile this now, and this is now dumped onto the FPGA.
As we can see, this is the FPGA board, and now this is the reset button and this is the direction button. Since the reset is an active low, since I kept it at low, the top 4 bits are 0. As I release this, as you can see, since the direction is reverse, it will start counting down. 10. See, as you can see, it's counting down, and then I'm gonna increase the direction. As you can see, the counting up has begun. The the four MSB bits are increasing, as you can see. Thank you.